Good morning, everyone. I hope that you are all fine and you are doing okay, and so am I. It's been 2 weeks since we met for class, and 2 weeks since we really did a lot of learning because of your exams. But we have resumed, and therefore, uh, we hope that you are going to resume and cover much of the syllabus that is remaining, even as we continue. So, welcome back to class sessions. Please also tell the rest that have not joined us to join us also, so that we may move on together. Well, as you have seen in your portal, today we are going to discuss the subtopic PC interconnection structures. PC interconnection structures. That is what we are going to be dealing with today. I'm hoping that we are going to finish it today. It's not a big area, so I hope that you are going to do it and complete it today. So I hope that I can be heard by everybody. If you cannot hear me, please ensure that you tell me so that I can do what is required. Let me share the screen so that we can begin the class for today. All right. So this is what we are learning today, PC interconnection structures. That's what we are learning today. Interconnection structures. In this subtopic, we are going to discuss in the different ways in which the computer memory, and here we are talking about the RAM, the computer main memory is connected to the processor, or the manner in which the computer main memory memories, assuming that a computer has multiple memories, are connected to a processor or multiple processors of a computer. So that is what we are going to be talking about. That's all it is about PC interconnection structures. It is the different forms and manners in which memories are interconnected to processors in a computer system. So there are 5 ways in which memories are connected to processor or processors in a computer system. And just before we even go into the 5 PC interconnection structures, it is important to know why processors and memories are interconnected. It is important to know why processors and memories are interconnected. Now, in our previous classes, we talked about the von Neumann architecture of computers, which is the basic architecture of computers up to date that is being implemented for how physical components of a computer are arranged. I remember you can remember the von Neumann architecture. I actually also asked it in the CAT. You can remember that. So in the von Neumann architecture, we talked about um, several parts of a computer, several components of a computer that top in the von Neumann architecture. We talked about the processor, the system buses. We talked about the memory, the input units, and the output units, right? And in the memory, we talked about the main memory, the RAM. We were also able to see a picture of how a RAM looks like, and there's something we said about a RAM in association to a processor. How is the RAM associated to the CPU or the processor? Someone can answer that. How is the RAM associated to the processor? How do they work together? Catherine, Dennis, Gashia, Duguna, Hannah Wangoi, Ian, Kipngeno, Lewis. Mwando. Chesire, how is the RAM associated to the process? How do they work together? How do they work together? Wangeshi, from our previous class. Hold data. Though that is very brief because all memories hold data. All kinds of memories hold data. So what is so special about the RAM? Because it's all memories hold data, not just the RAM. Hold data before execution, that is true. It holds data temporarily, that is true. So those are true arguments that what makes the RAM special and how it is associated to the processor is that the RAM temporarily holds instructions and data before and after processing. So the operating system loads all instructions before processing to the RAM, where the CPU can fetch them using as any kind of algorithm. It can be first in, first out, it can be last in, first out, it can be round robin algorithm, whichever algorithm, and it fetches the instructions from the RAM before execution, and also returns the output or the result of execution to the RAM, and the RAM holds the results of execution temporarily before it is now transferred to other output devices like the monitor, the speaker, or it performs a certain action like transferring a document to a printer, things like that, outputs. So that's how the RAM is associated to the processor, and therefore that is why we are talking about interconnection structure, because you need to understand now how the different ways in which the RAM is interconnected to the processor, the different ways in which that happens. So now we can now go now to PC interconnection structures. There are 5 interconnection structures, 5 modes by which RAM or RAMs is or are connected to a processor or processors. The first mode of connection is time shared common bus, multiple memory, crossbar switch, multi-stage switching network, and hypercube system. All right. So these are the 5 interconnection structures, and I hope that you have somewhere where you are noting down the short notes as we are learning. I'm assuming that you are not only listening, but you are also taking down some notes, even though the notes are there, but it's important to write as you go through whatever you're being taught, so that you can remember. So these are the 5 interconnection structures. Let's begin with the first, time shared common bus. Now, in a time shared common bus, the computer system consists of a number of processors. So that's the first characteristic of time shared common bus. There are multiple processors, all right? Multiple processors. These multiple processors are connected through a common path to a memory unit. So there are multiple processors, there is a common path, and there is one memory. Those are the 3 major characteristics of time shared common bus interconnection. Processor ni kadhaa, si moja. There are different processors, 2 or more. There are multiple processors. These processors are connected to one memory unit or one RAM, all right? And they are connected to one RAM through one channel. So there is one path for connection. There is one circuit for connection. Now, how does it work? So that is the physical structure of time shared common bus. Now let us look at the logical structure. The logical structure is how it works, how data is passed to and fro between the multiple processors and the RAM. Now the logical structure. The logical structure is this: only one processor can communicate with the memory or another processor at any given time. Only one processor can communicate with the memory or any other processor at any given time. Why is that so? That is so because there is what? There is only one path. There is only one channel of communication. All right. So different processors are connected to one memory unit, and all of them, all those one memory unit, they are connected to the different processors through one channel. There is only one channel of communication, and therefore that means that it cannot support multiple back and forth communication. It cannot support simultaneous communication. All right. So there is what we call serial communication. Serial as in SERIAL, serial communication. Serial communication basically means that a processor can only communicate to another processor. Uh, in other words, different processors cannot communicate together at the same time, or different processors cannot communicate with the memory unit at the same time. One processor, if one processor wants to communicate with the memory unit, it has to do so, and the other has to wait. Okay, so that is called a serial communication, one by one. There is no parallel communication. Also, there is no back and forth communication. Transfer operations are conducted by the processor that is in control of the bus at the time. All right. So what does this statement? I want you to follow what I am highlighting, because that's where I am deducing the points from. So what does this statement mean? Transfer operations are conducted by the processor that is in control of the bus at the time. This means that there is one dedicated processor. We always know that the processor is made up of two main parts, two internal logical main parts. That is a control unit and the arithmetic and logic unit. Those are the two logical main parts. The other is the RAM, and it's not a logical part, it's a physical part, and it's not part of the CPU. It's a separate part of the CPU, but it is considered part because the CPU cannot work without it. All right, but there are two logical parts of a CPU: the arithmetic and logic unit, the ALU, and the control unit. So there is one particular processor in this time shared common bus whose control unit is a dedicated control unit. All right, a dedicated control unit means that it is the one that manages communication for the whole system. All right, that manages communication for the whole system. That's what we mean by transfer operations are conducted by the processor that is in control of the bus. All right, so there is one dedicated processor that manages communication. All right, so when one processor is communicating with the memory unit, or vice versa, or one processor is communicating with another processor, any other processor wishing to initiate a transfer at the same time must first determine the availability status of the bus, and only after the bus becomes available can the processor address the destination unit to initiate the transfer. What that means is that one processor must have to determine that the bus is free. Remember buses, there is data bus, control bus, and address bus. Here we are talking about a data bus, all right? The one that carries data back and forth between a what? Between a memory, between a memory unit, between the RAM and the CPU. So the bus is the part of communication. This channel that we are calling the channel of communication is what we call the bus. It is the pathway through which signals pass. Okay, so a processor must, if it wants to communicate with the memory, it must first establish that the channel is free. All right, why? Because it cannot pass any signal, it cannot transmit any signal when there is already a signal from another processor or from a memory unit that is passing through it. All right, and that is why it is called time shared. I want you to relate these things, okay, so that you don't get lost or you don't get yourself to a place where you have to cram. That's why it's called time shared. Why? because all these CPUs and with that memory unit, all of these devices, the multiple processors and the memory unit, they all share the same system time. All right, they share, so they cannot. Only one can have one. Only one can go at a time because it is limited. There is only one path. That's why it's called time shared. Okay. So let's continue. A command is issued to inform. So if a processor wants to communicate with the memory unit, number one, what should happen? It should first check if the bus is free. All right, if the channel is free, because it cannot transfer signals if a channel is busy. Okay. Then the status of the bus is now sent to the processor. This is what we are saying. A command is issued to inform the destination unit what operation is to be performed, and the receiving unit recognizes its address in the bus. And responds to the control signals from the sender, after which the transfer is initiated. The system may exhibit transfer conflicts. I want you to take note of this: transfer conflicts. Since one common bus is shared by all processors, these conflicts must be resolved by incorporating a bus controller that establishes priorities among the requesting units. Now, so we have said that when a processor wants to communicate with a memory unit, you see there are different multiple processors. So if a processor wants to communicate with a memory unit, it first has to establish that the bus or the channel is free. All right. Now, if different processors at the same time request for connection to the memory unit, at the same time different processors request for connection a memory unit, that may result to what we call a transfer conflict. That's why I've told you to take note of that phrase, a transfer conflict. A transfer conflict happens when different processors require priority. They are all asking priority to be able to communicate at the same time. All right. So that's why we are saying that these conflicts are normally resolved by incorporating a bus controller. A bus controller is basically just an algorithm that enables the system to solve these transfer conflicts. So that if at time t1, processor P1, processor P2, P3, P4, P5, all of them at time T1 are requesting for communication with the memory, with the RAM. At that time T1, there can be what? A transfer conflict. So therefore, what solves these conflicts and ensures that each one of them is given priority at its own particular time, we normally introduce what we call a bus controller. A bus controller is the one that manages prioritization in a time shared common bus. So if I can ask you in an exam, what manages prioritization of transfer in a time shared common bus? It is this called a bus controller. All right, bus controller. It is the one that manages prioritization. So I want you to look at this. I want you to look at this diagram here, right? So when you look at this diagram, there's something very. It shows you the structure, the physical structure of time shared. So it has one memory unit. As you can see here, there is only one memory. Can you see it? Yeah, there is only one memory. Yeah, and then there are different processors. Can you see them there? Right? There are different processors, and they are all connected through one path. Can you see this trunk? This one is called a trunk. All right. I think if you have done anything, introduction to ICT, you were introduced to the topic of computer networks. And in one of these networks, there is something we call logical topologies, physical topologies. All right, physical topologies. And there is one of the physical topologies you called a bus topology. I think you can remember that, a bus topology. So basically, a time shared common bus works like a bus topology, all right, where there is one common path This is the common path, and it's called the trunk. It is the one which supports all signal transfer from CPU to memory or from CPU to CPU. All right. Why CPU to memory? CPU to memory because of the reason we say that the memory holds data uh, um, temporarily before a CPU processes or executes it. But there can also be communication between CPU and CPU. When that does that happen? During when there is a what we call a switching of tasks. Okay, CPU in a multiprocessor system in a particular time, let's say time T1, different tasks can be switched between different processors depending on depending on the on how depending on how much system time one particular task takes. Okay, because there can be those there can be those tasks which take little time, so they can be executed and they are taken back to the memory. But there are those uh, tasks that take a lot of system time, so they have to be switched back and forth between different CPUs. All right, so that can be executed between different CPUs, especially when we are dealing with applications that are too big. Yeah, they can be when they are in play, when that application has been opened in a multi-processor system, it may not be one processor that is processing it. Different threads. I think you talked about you have done operating systems at some point. Different program threads can be switched from one CPU to another to enable so that one CPU may not be overwhelmed. Anyway, that's a lot of information. What I'm just trying to say is that communication can happen from CPU to CPU. Communication can also happen from CPU to memory unit, but this communication is all goes through one channel. All right, and therefore for a CPU to communicate with a memory or for a CPU to communicate with another CPU, it first has to check that this trunk haiko busy. It has to ensure that this trunk is not busy. And busy here we mean that it doesn't have a signal. Okay, if it has a signal, it will be put on hold, and it is put on hold by what? By the bus controller. So signal ikiisha, the next signal yenye imepewa priority then can pass through the signal iende mahali inaenda, whether inaenda kwa memory ama inaenda kwa CPU ingine. Okay, so that's how a time shared common path is. Now, what do you think? Let me just have that. What do you think is the disadvantage of this kind of system where we have different processors, they are connected to one memory unit, they share one path, they cannot send data simultaneously, they have to wait for each other? What are some of the disadvantages you think can be experienced in such kind of a system in the time shared common bus? From that knowledge, what are some of the disadvantages? What are some of the disadvantages? It might take too long for execution of data. Yes, there is an issue of system speed. That is true. System speed is compromised. It is slow because there is only one channel. Yeah, that is true, Ronnie. System speed, still the issue of system speed, it is slow. All right. Then there is also another disadvantage of transfer conflicts. If there is no bus controller, there can be a conflict where signals are competing for resources. Now, when in a computer system, when different parts or components of a computer system are competing for common resources or for shared resources, there is a fatal condition that happens. That condition is called what? when there is a competition of common resources, the system may come to a fatal halt. There is no processing, there is no memory activities happening, there is no signal that is being passed. Ni kama machine may freeze. There is nothing that is happening. That condition is called what in ICT? Deadlock. That is true. It is called deadlock. Deadlock is the fatal halt of processing and memory activities in the computer. All right, and this is a thing that can be experienced in the time shared common bus. All right, it can be experienced. Why? Because if there is transfer conflict, as we saw here, if there is transfer conflict, then that means that the signals are competing for the same trunk. They are competing for that part, and therefore deadlock will happen. In other words, hakuna yenye itapewa priority, zote zimekwama. Okay. So there is no processing happening, there is no memory activities that is happening. Basically, the computer has come to a freeze, come to a halt. All right. And the method for releasing a computer from deadlock is doing what? Restarting it or shutting it down. Yeah. But of course, normally it doesn't happen mostly so much because the operating system has different algorithms, countless algorithms of managing deadlock. But if it happens, then it is a fatal condition, meaning that the system has been overwhelmed by a competition of resources. All right. So also another disadvantage of this system is sorry. Another disadvantage of this system is that different memories, all right, one memory may not be able, or we cannot use a memory that has a small space. We cannot have a memory that has small capacity. So you can't use a 2 GB RAM for a time shared common bus, because how is it able to serve all those processors? Right, so you need a bigger memory with bigger capacity, right? Yeah. And you see, the more the RAM, the more expensive the machine, right? For instance, if you go out there and find a computer that has 2 GB RAM and 500 GB hard disk, they sell you at 25,000. You go somewhere or in the same shop, you get 4 GB RAM and 500 GB hard disk. So hard disk has not changed, but RAM may change 4 GB. All of a sudden, you hear the price has hiked to 30,000 from 25 to 30. It's like 2 GB RAM itself is 5,000. They have just done that because of what? Just because of the RAM. Because RAM is a shared resource in the machine. And when the capability of the RAM and the size of the RAM has been increased, the price of the computer system increases also. All right. So if you have 5 processors and each is running at a speed of 2.6 gigahertz, 5 processors, all right? So these 5 processors cannot be supported by a 2 GB RAM or a 4 GB RAM, all right? They require a 16 GB RAM, a 32 GB RAM, and if they are not even there, you'll have, the point is that you'll require a lot of memory. You'll require a lot of memory, and the more you increase the memory, the more expensive the system, all right? So that is another disadvantage, but there is an advantage. There is an advantage. One of the advantages is, let's go back here. Let's see. One of the advantages is that this system is simple to implement. It is simple to implement, and therefore reduces what we call complexity. All right. So it is simple to implement. It is not a very difficult system for the operating system to implement or work with. It is a very simple structure. That is one of the advantages. All right. Then now let's go to the other one, multi-port memory. So tukienda hivi ukiangalia, remember hizi venye zinakaa, and you are able to explain all of them. All right. So this looks like what? Looks like a bus topology. Yeah? And we've already discussed how it works. All right. So multi-port memory. A multi-port memory employs separate buses. So there is no one dedicated path. There are different dedicated paths. So it employs separate buses between each memory module and each CPU. In this one particular sentence, we already have three characteristics. The first characteristic is that there are multiple memories, multiple processors, and multiple paths. All right? Multiple memories, multiple processors, and multiple paths. So if you have two processors, you will require two memories. In other words, each processor serves, in other words, there is an equal proportion of processor to memory. All right. So 4 processors, 4 RAMs, 5 processors, 5 RAMs, 6 processors, 6 RAMs, 1, 2, 3 processors, 3 RAMs. All right. So and there is a one dedicated path from one CPU to one memory. There is one dedicated path. In other words, a CPU can communicate to a memory unit without sharing its path. In other words, it's not even cut. It is that they don't share paths, right? They don't share paths. A CPU communicates with a memory unit in its own dedicated path. A CPU communicates to another CPU in its own dedicated path. So that is basically the idea between multi-port memory. Now, why is it called multi-port? I want you to take notice of the word port because there are segments of interconnection. All right, a port is a what? Is a point of connection. All right, like the way you can say a USB port or a VGA cable port. All right, or a serial cable port. A port is a what? A point of communication. An audio jack port, right? We don't call them holes. We call them ports. A port is an interface between devices. All right. So why is it called port? Because these buses, I want you to now look at this picture. In this picture, these lines, the links that are connecting CPU, kama ukiangalia hapa kuna hii CPU, kuna hii, kuna hii, na kuna hii. So ni ngapi? Ni 4. And then kuna memory 1, memory module 2. MM stands for memory module. Memory module ni kama RAM moja, one single piece of RAM, memory module. Okay? Memory module 3, memory module 4. So CPU 4, memory 4. In other words, the number of processors is equally proportionate to the number of memories in a multi-port memory system. Angalia hizi links, hizi lines. Where are the ports? The ports are these dark areas. These dark areas that you can see huku. None of these dark areas. These dark areas are what we call the ports. These ones that I'm highlighting. These are the ports. A port is a point of connection, all right, between links, all right? So if CPU 1 wants to communicate with memory module 1, it has to go through the port and then go through there. Okay. If it has to communicate to memory module 2, it has to go through how many ports? 1, 2, then communicate to memory module 2. If it has to communicate to memory module 3, it has to go through how many ports? 1, 2, 3, and then communicate. If it has to communicate to memory module 4, it has to pass how many modules? Ports 1, 2, 3 also, and then communicate to memory module 4. All right. So how many ports can you see? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. How many are those? Those are 12. All right, those are 12. So when you are designing, when you are drawing a multi-port memory, you have to have the number of CPUs or the number of memories times 3. Okay, because the last ones don't need ports. Why? Can someone tell me why the last ones don't need ports? Why does these buses don't require ports? Why are there no ports in these buses? The memory module 4. Why are there no buses? Why are there no ports? Why are there no ports in the last in the links or the buses of interconnection of the last memory module? It's where the process ends. Somebody else? It's a good trial. Basically, the reason why there are no ports in the last memory module is because there is no overlap, or there's no crisscrossing of buses. Alright? Kama ukiangalia hapa, the reason why kuna port hapa ni kwa sababu there are two different. Ukiangalia hapa kuna each it manages this. The port at that point manages how transfer happens, where data buses crisscross. So when there is no crisscrossing of data buses, then we don't need ports, okay? Because ports are meant to join. Ports are meant to join different things. All right. So basically, to understand it better, let me go through the notes now, so that you can see now how it works. So we have already determined, identified that the physical structure works with the number of CPUs is directly proportional to the number of memory modules, and each uses a dedicated path. There is no one shared path. Each uses a dedicated path. So this is how now it works. A processor bus consists of the address, data, and control lines required to communicate with memory. Of course, this is common knowledge. A processor in our king in address bus, data bus, and control bus. Okay. The address bus is to send the address of the data from memory unit to processor. Data bus is to send the data chunks. We also call them data tokens. Tulisoma hizo vitu kwa von Neumann architecture tukisoma about buses. And then control bus is a bus that sends one-way signals between a processor and a device. All right, one way. There is no back and forth. So in common knowledge. But now this is how it works. The memory module is said to have 4 ports here, just like here. 1, 2, 3, 4. All right, between 4 CPUs and 1 memory. Kuna how many? Kuna 4 ports. That's what it means with this system. The memory module is said to have 4 ports, right? And each port accommodates one of the buses. The module must have internal control logic to determine which port will have access to memory at any given time. All right, and then let me also finish with this. Memory access conflicts are resolved by assigning fixed priorities to each memory port. I want you to discover how ports is being repeated every time. Okay, so the memory module has logic to determine which port will have access to memory at any given time. Then the priority is determined at the port. All right, and this is how the logical, this is how now a multi-port memory system works. In the time shared common bus, you remember that there was a bus controller that has to be installed, that will manage communication in the trunk, si ndio? Kunafaa kuwa na bus controller. Hiyo bus controller ndio ina manage prioritization. All right, and so here we don't need a bus controller because there is no one dedicated path. What we just need are the ports. So all prioritization happens at the ports. Okay, why is that so? Because this is so because of this. Angalia, for instance, CPU1 inataka communicate na memory module 1. Okay, CPU1 wants to communicate with memory module 1, but at the same time memory module 2 wants to send an item to CPU1 at the same time. So which path is memory module 2 going to use to send that nini? Si itatumia hii path and then hii path. That's right. Yeah. Now CPU1 to communicate with memory module 1 itatumia which path? Itatumia this path and this path. Now kumbuka, at the same time when this one is sending, this one is also sending. All right, when CPU1 is sending to memory module 1, at the same time T1 memory module 2 is sending to CPU1. So how is priority at the ports? All right, so for time shared common bus, prioritization is managed by the bus controller, but for multi-port memory, prioritization is managed by the ports. It is the ports that manage priority of signals. So hii itatuma, are we together? It will send, but this port will communicate with this port, right? This particular port will communicate with this port using what? Address bus. All right, an address bus. Address bus is the one that carries the address of a data token. All right, so this port will communicate with this port, and this port will inform. I'm using those literal terms for your understanding. This port will inform this port that there is already a signal that is passing through. All right, there is already signal that is passing through it. Okay, so hii signal itakuwa held hapa. Okay, itakuwa held hapa kwa hii port. All right, because there is already signal that is passing through here. So this port, after this port has informed this port that there is already signal passing through it, then this port here that I've highlighted will hold the signal until this signal repeated. Okay, until that signal is done, the transfer is done, and then now it can release that signal, and then there will be a connection. All right, there will be a connection. Put together. So they work like roads. They work like roads, and they work like police officers that stand at the junction of different roads. Okay, these police officers communicate to one another. You know, release traffic, hold traffic, release traffic, hold traffic. All right. So those how the ports work. The ports work like traffic policemen. All right. Their work is to hold traffic or release traffic depending on how much traffic is on the other side. So kama kuna transfer ina happen hapa, hii port ya hapa itaambia hii port ya hapa there is communication happening. So this port will hold communication, and then when this port, the transference happening between this port is over, then now this port can release the signal. All right, then there is now connection. So this is how the multi-port memory works. I hope now you understand. Okay. I have tried to explain using simple words so that you can understand, because here now we have a lot of hard or difficult words. Now, the advantage of multi-port memory is that the high transfer rate can be achieved because of multiple paths. So The multi-port memory is not slow because there is no single dedicated path. There are multiple dedicated paths. Okay, so high transfer rate. This just means the speed is faster than a time shared common bus system. Another advantage is that there is also more efficient prioritization. Remember, and that which means also that there will be less transfer conflicts. Okay, remember in the time shared common bus, there is only one bus controller managing all the traffic, but here we have different ports. Okay, we have different ports. We have different ports at every single instance. We have different ports that connect the different buses, right? That stand at the junction between the different buses. Okay, so these ports manage prioritization, and a port cannot be overwhelmed. All right, a port cannot be overwhelmed because there are different other ports. All right, so there is more efficient prioritization, meaning that transfer conflicts are fewer and fewer. The only disadvantage is that it requires expensive memory control logic and a large number of cables and connectors. Why? Because of all these connections. Yeah. So it requires a lot of cable. It also requires, and also it is more complex to implement. It is more complex to implement. It is more complex to implement. Hata ukiangalia tu structure yake venye inakaa, it's a more complex system than the timeshare. But do you realize that the more complex the system, the better the transfer rate, and the better the prioritization, the more efficient the prioritization. So that's the disadvantage. It's complex to implement, and it's also costly on the number of cables that have to be used. All right, that have to be used. Right? Because why are we talking about cables? We are talking about cables because for all this to happen, you remember we said we talked about networking. In introduction to ICT, you were told that a computer network is a connection between different devices to facilitate data transfer and information sharing and sharing of resources. That's right. Yeah. So a memory module, see, it's a resource. A memory module is a resource. A CPU is a resource. A CPU is a resource. Also, the data being sent from one CPU to another CPU or from one CPU to another memory, it's a resource. So all these resources are being shared. So for all this to happen, you need cables. All right. Because imagine, because this can actually happen that in a device, there is a device that hosts a CPU and a memory. Another device hosts a CPU and a memory. Another device, a computer, holds a CPU and a memory. Another device holds a CPU and a memory. So all these devices to be interconnected to form a multi-port memory, you need cables. All right? You need cables to connect them. So that's why we are talking about a large number of cables and connectors to implement. All right. Let's talk about the crossbar switch. The crossbar switch. All right, let's now discuss this. The crossbar switch organization consists of a number of cross points that are placed at intersections between processor buses and memory module paths. Let's look at this diagram here. So also in the crossbar switch, similarly to the multi-port memory, the number of processor is equally proportionate to the number of memory modules. All right, but the difference is that instead of having the different ports for each connection, like here you have, unaangalia hapa unapata kuna let's say kuna data buses 4 zina connect to memory module 1, right? Hapa kuna data bus moja. Can you see that? Hapa kuna data bus moja, lakini hapa kuna data bus 4. So there is only one bus between a memory and a processor, but in a multi-port memory there are four. It doesn't have to be four. Kama processors ni tano, memory hizi buses zitakuwa tano. Okay, kama ni sita zitakuwa sita, kama ni tatu zitakuwa tatu. So the number of buses are equally proportionate to the number of what? To the number of CPUs. All right, but here we just have one for one. You notice that one for one, one for one. Now again, here we are having a port, right? We are also having a port. See those ports? These ports also, as in multi-port memory, even in crossbar switch, they are the ones that are responsible for prioritization of transfer. And therefore, if memory 1 wants to send data to processor 1, when it gets to the when that data signal gets to the port, it is this port that has to ensure that there is no presently existing signal that is already passing through it. So port ita hold ama ita give priority based on whether or not there is a signal already passing through it. Okay, so it works basically like the multi-port memory. The only difference is that there is only one data bus for one memory, one data bus for one memory, one data bus for one memory, right? So that's how it works. So for instance, memory 2 wants to communicate with processor 3, itapitia ports ngapi? 1, 2, 3, 4. But at every single instance kunaweza kuwa na, for instance hapa kwa hii port already kuna signal inapita, so ikifika hapa itakuwa held. Alright, itakuwa held. But ile wakati iko held, remember hapa sasa imekuwa free, si ndio? Hapo imekuwa free, so this one is now free to release. So memory 4 inaweza kuwa ina send data hapa hivi, so iko free, but ikifika hapa ipate kuna data imekuwa held, ingoje. So zinaenda zikingojana, they go waiting for each other. Alright, they go waiting for each other, and that's how they work, because there are no four paths, there is only one path for each memory module. So that's what that's how this works, right? This is another way of looking at it. For those who do electronic engineering, for your colleagues who do electronic engineering, they understand this. So this is a closed circuit, this is an open circuit. Open meaning, open just means that there is no data signal that can pass. It's like when you switch off the switch, when you put off the switch. And this is a closed signal, meaning that a connection has been established, there is signal passing. All right, yeah. The advantages and the disadvantages for multi-port and the crossbar switch, they are the same. All right, because of ports there is efficient prioritization and such things. Then there is multi-stage switching network. Now this one is a little bit complex, the multi-stage switching network, but let's discuss it. It is formed by cascading multiple single-stage switches. The switches can then use their own routing algorithm or controlled by a centralized router to form a completely interconnected network. There are three types of multi-stage. Just before we go that, let me explain this. Cascading multiple single-stage switches. This just means that in the different points of communication, there is a device there that works like a gate. Now here we are not talking about ports. We are talking about a particular device that can work as a gate or a switch or a router. Alright? So kama hapa kuna CPUs ngapi? 1, 2, 3, 4, 5, 6, 7, 8. Usijali na hizi numbers. These are called binary numbers. Nitawafunza at the end of the unit. There is a topic for number systems. Alright, so nitawafunza hizi. numbers. These are just binary numbers. I'll tell you at the end of the unit how they are manipulated. But basically, the interest is here. The CPUs. How many CPUs are these? 1, 2, 3, 4, 5, 6, 7, 8. And also there is a equal number of memory. No, there is an equal number of memory. So there are in between. There are, this is A1, A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. These are devices that function as gateways or gates. And the function of a gate is basically to allow through signal, and also to function as a router. To route is to determine the best possible path for a signal. All right. And switch is to determine the address of the recipient. This way a switch works, the normal switch in a computer network. You learned about the different networking devices, switches, hubs, gateways, routers, such things. Yeah, and even modems. Yeah. So here there will be a device that will work like a switch or a router. Yeah, it's just a gateway. All right. And that device, the function of that device is to determine, number one, the best possible route. All right, the best possible route from one path to another. Also to determine the address of the recipient. Nataka, you get this very well. And these things are not hard because you already did computer networking. So it's very easy to kind of join all this information together and make sense out of it. So, for instance, let's say CPU 000. Again, I've said don't worry about these binary numbers. I'm going to teach you how they are manipulated. But for now, let's use them just as they are, like indicators. When we could just say CPU A, CPU B, CPU C. So if CPU 000 wants to send data to RAM 001, there are different paths. Ukiangalia hapa kwa kwa crossbar switch, there is only one path. Can you see that? One path, one path, one path. If it wants to send from here to here, one path, one path. And you see that? But so haziendi hizi back and forth. Utapata ati memory 2 ikitaka kucommunicate na P4 ati itaenda hivi, ikifika hapa ipelekwe hapa, ikifika hapa ipelekwe huku, ikifika hapa ati iende hivi. Yeah, and that way in a very haphazard manner. No, it goes in straight lines. Kama ni P4 itaenda hivi. Okay, so at every port itakuwa inaangalia kama kuna signal. Kama kuna signal, the switch, the port remains open, meaning signal cannot pass through. Kama hakuna signal, the port is closed. Port is closed, or meaning, so basically what I'm trying to say, in crossbar switch and also in multi-port memory, there is no haphazard movement. It moves in straight lines, okay, from one point to another. Are we together? But the difference with that and multi-stage is there is a cascading. Cascading meaning that they can crisscross. Why? Because the work of this gate, which functions like a router or a switch, is basically, number one, to determine the best possible path for a signal, and number two, to determine the recipient of that signal, the recipient address of the signal, like a switch does. So 000 wants to communicate with 001 here. CPU 001 wants to communicate with memory 001. Now, there are different paths that signal can pass through. It can pass through from here to A1, from A1 to B1, from B1 to C1, and then from C1 to 001. Can you see that? There is also another path. There is there to A1, there to B2, from B2 to where? From B2 to from here to A1, from A1 to to B2, from B2 to C3, and by the way, these things have to be interconnected from, there have to be interconnections here, right? So I forgot drawing these interconnections here. There should be interconnections here, right? Kunafaa kuwa na interconnections huku. Okay, so it can move from A1 to B2, from B2 to B1, from B1 to C1, from C1 to C2, and from C2 to 001. In other words, there are different paths. It does not have to move in a straight line. Why? Because it is the work of the gate to determine the best possible path. How does a router determine the best possible route for a signal? By checking all the possible routes, and the one which does not have by checking the one which does not have much bandwidth or much signal traffic. So the path that is lesser busy or more idle is the one that is normally chosen. Okay, is the one that is normally chosen. So the advantage of this system, so we've now gone to the advantages and disadvantages. The advantage of this system is that there will be no holding of signals at a point. Ukiangalia hapa inaweza fika hapa ni kuwe held kwa port. Kwa nini? Kwa sababu already kuna signal inapita hapo. Okay, but kwa router, for instance, if all of us are using Wi-Fi, let's just talk about the normal router. Okay, if all of us are using Wi-Fi, there is nobody who's going to be getting lesser privilege. All of us are getting privilege. Why? Because each person, the router, determines the best possible path for every device in the system. So no one, you as the user of the system, you have a feel as though you're the only one using the system, because you can access the internet, you can access other devices. At the same time, other people are accessing the same devices you access. So if you're using a Wi-Fi, there's a router, and there are different routers all over the world. All of us can be accessing Facebook or Gmail at the same time, and nobody feels as though there is somebody who has more control, right? Because the work of the router is just to determine the best possible path for each device, right? So basically, there is no holding, like when you're using Wi-Fi that is being implemented by a router. No signal is being held anywhere. All right, it can be slow, yes, but it is not being held. Okay, it is still moving, it is in motion. All right, so there is no holding. That is the advantage of multi-stage. All right, multi-stage switching network. There is no holding of signals. Signals are always in motion. All right, so that also increases what? Transfer rates. Tuko pamoja? So that is it about the multi-stage, and I hope that you are understanding. Then let's go now to this last one here, the hypercube interconnection. Hypercube interconnections, it's a topology used to connect multiple processors with memory modules and accurately route data. Hypercube networks consist of 2 raised to power m nodes. These nodes form the vertices of squares to create an internetwork connection. A hypercube is basically a multi-dimensional mesh network with 2 nodes in each dimension. Due to similarity, such topologies are usually grouped into a K and D dimensional mesh topology family, where D represents the number of dimensions and K represents the number of nodes in each dimension. Now, basically, hypercube interconnection uses what we call multi-dimensional communication. Multi-dimensional communication. Now, these are the kind of networks that are able to support services, GSM services. GSM just stands for Global Service, Global Service Mobile Communication, GSM. All right. So multi-dimensional networks are able to support services like holograms. All right, holograms, things like that. These networks are also able. These kinds of systems, they're able to produce holograms together, because they can emit multi-dimensional signals. I think all of you understand hologram, yeah? A hologram is basically an image that is 3D in nature, all right? Meaning that you can see every side of it as though it is a real object. That's a hologram, all right? So they can produce holograms, and these systems are normally used when we are when we are dealing with simulation of things like simulation of cars, simulation of architecture, when architects are trying to test the strength of systems. What will happen if a system is the strength of a building? What will happen if a building is hit by a wind? What is the strength of a system? They are able to see that building holographically. Okay, they are able to see it as a simulation, as a holographic simulation. All right, as a holographic simulation. So hypercube interconnection, basically they support multidimensional signals. They are able to produce multidimensional signals, and therefore they support things like holograms. All right. The advantage of this is that signals take up more real forms. Signals take up more real forms. All right. Yeah, signals take up more real forms. So this is what we call the hypercube interconnection. So don't worry about this, the 2M nodes, the K array and D dimensional. Don't worry about them. What you need to know in hypercube is that they emit multidimensional signals, and these signals can be projected holographically. Okay, yeah, so that is it about the PC interconnection structures. Any question before we move on? Any question before we move on? All right, I can give you like it's 12:25. I can give you like 15 minutes, just a small break, and then we move on. Is that okay? We have already done 1 hour, so I can give you a break and then we move on. I hope that's okay with everybody. A 15-minute break, then we move on. Okay, then let's have a 15-minute break, then we continue. All right, we are back. So I want us to do an introduction to chapter 2, input-output organization. Now, basically, we know what input devices are and what output devices are. Input devices are devices used to enter data or instructions, or to feed the computer with data and instructions, and they can things like keyboard, mouse, light pen, joystick, and scanners, magnetic and optical scanners. Output devices are devices that are used to give out information or the results after processing. The results after processing. The results after processing. So we already know that. We already know that. So we will need to talk about input-output modules. Right. Now a module is we also call it the I/O module. It is a device that acts as a connective bridge between a computer system and an I/O or peripheral device. It is a device. A module is a device. A module is a device that acts as an interface between an input device and the computer system, or an interface between an output device and a computer system. All right. Now, there are different tasks, and you're going to understand this. It's a very simple concept. So I'm going to show you them with pictures a little bit later after we read these notes here. Uh, what is the? Or let me just go. Let me share with you a screen here so that you can see what I'm talking about. I/O module. A module is a point of interaction between a system and a peripheral device. This peripheral device can be an input device or an output device. A peripheral device is basically a device that is not hosted in the computer system, meaning that it has been hosted within it is outside the computer system unit. It is not mounted on the motherboard, or it's not within. So a peripheral device can be like a keyboard, a printer, an audio, an earphone. That's a peripheral device. A mouse. All right. Those are peripheral devices, things that are outside. They are connected to the computer from the outside. So an I/O module, the basic function of an I/O module is to offer uh, connectivity, or to provide interface between a peripheral device and the computer itself. All right. So, for instance, let me show you some kinds of modules that you are going to see that you can actually look at. Let me just pull a screen here which you can see. I want to give you an example here. Yeah. Uh, let's think about. Let me share this screen here so that you can see what I'm talking about. I want to begin with the simplest that you will understand and you will connect with very easily. Where is this screen? All right, let me share it. Sorry. Just a minute. All right, there we go. Still loading. It's still loading. All right. Now I want to I think when you see that those images there, you can relate. You know what these are. This is an audio splitter. An audio splitter is basically a device that enables you to connect two different headphones or earphones, and you can actually listen to the same content as connected to the mobile phone, to the tablet, or to your laptop, or even to the desktop PC. You can actually share with somebody. As you can see, these are audio splitters. I hope there is no one who doesn't know this. Yeah, you are young people, so you deal with earphones a lot. So if you want to share with someone, you want to listen with someone, um some content in your phone or your tablet, instead of you sharing an earphone, mmoja anaweka kwa hii masikio, mwingine anaweka kwa ile masikio ingine. Everyone can use their own earphone, and both of you plug both of y'all's earphones to the splitter. All right. For instance, look at this one. So this is where you connect, and these edges. Sorry, this yenye naka U, the U shape. Someone plugs the earphones there, their pair of earphones, and the other one plugs their pair of earphones there. Let's look at another. Here is another. Yeah. So this end here. Sorry. This end here, I hope that you can see the movement of my cursor. This end here is the one that you plug into the device, and then both of you, but this one is for recording. One is for input, one is for output. All right, so input, output. One for listening, one for recording. Let's have another. This one. Yeah, so this is for plugging into the device, and this is where one of you can, all right, this is also for recording. This is for listening, this is for recording. I want one. Yeah, this one. This is also for listening, this is for recording. But this listening recording, I want one which is for both. Let me have audio adapter. Yeah, like this one. So, like, look at that. So one of you, both of you can actually listen to the same content, each of you using their own set of earphones or ear plugs. So this is an earphone adapter. This is also an earphone adapter. Both of you can listen, right? So all this, ukifunguanisha hapa, ukifunguanisha plastic, inside here, you will find some cables and other circuits. In other words, there is something happening here. This is not just an empty space. Okay, you will actually find that there is some form of connectivity that has been done inside here to ensure that both of you can listen to the same things. Now, this is an example of this is an example of a what? Is an example of a more of an input output module. Now this one is an output module. Okay, the basic work of a module is basically to offer an interface, a bridge, a connectivity bridge between a device and peripheral device. A device here, I'm talking about a machine and peripheral devices. So this one, you'll connect it to the laptop, and then now that laptop, you can now connect it to the earphone. All right. So these are what we call an output module. All right. It offers a bridge of connectivity. Now let's see other, at least now you can relate to that. Now let's see other kinds of other kinds of modules. So I'm just going to have here input output modules. That way, then we are going to see some kinds of modules. Sorry. All right. So there we go. Let me see if this is well shared. Right. So these are other kinds of input output modules. There are different kind of modules depending on what you are connecting to your computer. All right. Even TVs. Some TVs come with some modules for you to be able to connect some devices like if you have a game set, a game kit, you might want to connect it to the TV. So the TV will offer some kind of module, or you can buy a module for your game kit so that you can connect it to your screen. Yeah, modules are just for connection. So if you look at these, there are different kinds of modules. Ukiangalia hapa, this is basically an module. This is a module for connecting. These are called Rj45 ports. All right, Rj45 ports are basically ports to connect Ethernet cables. All right, Ethernet cables, and especially this is a module that is normally used when you are connecting Ethernet cables to a server. All right, Ethernet cables to a server. So they have first to go through the module, and I will tell you why in a few minutes. Right. Let's have another module. Let's have there's one I've seen for video card. Video card, where is it? This one, right? This is a video card interface. Yeah, this is a module. Na utaipata kwa kompyuta mingi, of course not on the laptops but on the desktop. Most desktops have this kind of module. Okay, for normally video, for this is a video card and it comes with a module. So this module is for video images, right, that come through a video game kit. Let's see another module. This is another module for video games. Now, I've just tried to search for that. Now, when you look at how a desktop computer works, or even a laptop, utapata iko na ports, right? So these ports, a port is basically where a cable goes into a system. So if you look at this, I think this is easier to look. I want you to consider this. There is a place for serial keyboard connection, serial mouse connection. There is a place for USB. There is a place for serial ports. Now these are parallel ports, keyboard and mouse parallel ports. These are serial ports for printers. There is also a parallel port, just like this one, for parallel printers. There is a game port. These are audio ports. Now, behind all of these ports, there is a module. Okay, so ukifunguanisha machine uangalie nyuma hizi ports zote zenye ziko hapa, hizo USB zote utapata ndani kwa motherboard, where these ports are behind them, there is actually a module. A module is basically a point of connectivity. It's an interface, all right? A module is just an extension. So ukifunguanisha machine utapata it is not just a hole, utapata tu ni hole. This is not just a hole, all right? Inside it, beneath it, or underneath it, or behind it, there is actually some form of circuitry that has been enclosed. I hope you understand that, and I hope you have observed that probably in your interaction with computers in real life. Yeah, there is actually a circuitry behind it. So ukifungua USB, ukifungua the machine itself, utapata nyuma ya USB ports hizi hapa, nyuma hizi USB port, it is not void, it is not empty. There is actually some form of circuitry behind it that has been enclosed. Okay, and that circuitry is what now we call the module. All right, it is that module that enables communication to happen between the device that is being inserted there and the machine itself. Okay, so now this takes me back now to this takes me now back to let me stop sharing this. This takes me back now to the functions of an input-output module, and there we go. So some functions of why does a computer require input-output modules? So it is not just enough for a device to be connected to a port. Remember the difference between a port and a module. A port is the literal point of connection. It can be a serial port, a parallel port, a USB port. Okay, it is the literal point of connection. All right, but a module is what is behind that port, which facilitates communication between the device that has been connected into the port. All right, so what is the function of a module, right? The function of a module, number one, is processor communication. Basically, this is just the work of processor communication. This is basically to accept and decode commands sent by the processor, reporting of current status, yeah, and also recognize the unique address of that device that has been connected. So if the CPU wants to communicate with that device that has been connected to that port, the port that is being hosted by that module, the CPU will do that communication through that module. So any communication coming from the processor, all right, to that device goes through that module. Okay. Then there is device communication, right? Device communication is basically for that device to communicate with the processor, right? To communicate with the processor. For instance, when you plug in a USB port, all right? When you plug in a USB cable, a USB device, or a USB media device, a flash disk or something like that, when you plug in the USB flash disk or media device or the cable, what happens is that the processor will have to detect the presence of an additional device. All right, the processor will have to detect the presence of an additional device. What helps the processor to detect is the module. Without the module, it's not able to detect. And that's why normally sometimes when your machine is not working right, like you plug in your USB but your machine cannot detect your USB, or you plug in your earphones but your machine cannot detect your earphones, the way to activate the module, to ensure to make the module to be able to communicate with the CPU, is to install what? Drivers. So you can install Realtek audio drivers if your machine cannot detect your earphones. You can install Bluetooth drivers. You can install you can install drivers for all these different devices that you want to be using. All right. You can install drivers for printer drivers. You can install drivers for USB. Though most of the time USB is plug and play, but if at all there is a issue that it cannot detect, you may want to update your drivers, okay, your USB drivers and such things. So these modules are activated by those drivers that you install. I hope that I'm not talking. It's not. I'm not talking of strange things. Yeah, I think you've heard about drivers. Yeah, so you install drivers so that this module can communicate with the CPU. All right, that's what we talk about device communication. But again, as I said, these things are normally plug and play. So if you install an authentic version of an operating system like Windows, you install an authentic version, it normally comes with built-in drivers, yeah, like drivers for audio, drivers for USB, drivers for DVD writer. If your machine has a DVD reader, it comes with all those drivers. But if at all there is some of these devices that you want to use, but you can't use them because the machine can't detect them, unaweka microphone haidetect, unaweka nini haidetect, unaweka hizi peripheral devices that you want to use with the computer na machine cannot detect, then you have to install that driver, all right, for that particular device, all right, a universal driver, meaning that it can support that device or others of the same nature, all right. So that is one of the functions of the second function of the module, to facilitate device communication, okay, so that it can be detected. Then control and timing. An I/O module is capable of managing data flow between a computer's internal resources and any connected external devices. So control and timing, it is that module that controls how data flows from that connected device to the machine itself. Then there is this concept called buffering, and this is a very, very important uh, function of an I/O module, buffering. Now, we are going to go into something called memory hierarchy. We are going to go there, but just for an introduction, there is a special kind of memory called buffers. There are three kinds of special memory: buffers, registers, and cache memory. Okay, and there is a special kind of memory called buffer. A buffer is a temporary memory that holds data and information between an input device or an output device and a computer. For instance, I want to give you an example. Sometimes you may find when you're using your mouse, uh, let's say you're using the normal mouse, not the mouse pad, but the normal hand mouse. When you're using the mouse with your machine, for instance, sometimes the system can be slow such that you click something but you don't see it being clicked, or you select something but you don't see it being selected. But for instance, if it is selected, if I select here, if my machine was slow at this moment, it may fail to show me it is selected the blue way, the way it has shown that in that blue color. But if I just leave it for a few seconds, itajiselect yenyewe. All right? It normally happens. I think you've experienced this even with your laptop or with your computer. What causes the machine to be able to know that there is an operation that has already been done? All those operations or instructions that have already been done but have not been executed are temporarily held by a buffer. So all these modules have some form of storage called buffer, whether it's a USB module, whether it's an audio module, whether it's a printer module, whatever module for whatever input output device you're using, it has a special memory in it called a buffer. And buffers are used to temporarily hold instructions, especially when the RAM is overwhelmed or when the processor is in the midst of executing other instructions or tasks. Okay, so the buffer is able to allow temporary storage. It's just like a printer. For a printer, you can, for instance, if I go to file, let me say file prints. I hope you can see what I'm doing here. So file prints, right? Then I want to print every page, but I want to, I'm sorry that this one is behaving that way. And I want to print how many copies? Let's say even 100. Okay, let me even have 200 copies. I want to print 200 copies of these notes. Yeah. If I click OK, and I exit this document, all right? I click OK and I exit the document. Close it document, all right? The computer will still print. I hope you know that. The computer will still print, all right? As long as there is connectivity. As long as nilimaliza click OK, meaning that there is a print instruction that has been sent to the CPU. Nikimaliza tu click OK hivi, printing will start. Even if it will not start immediately, it will start whenever time it will start. Even if I close that document. Why? Because there is already a command that I've already given the CPU. So this command is normally held where? At the printer's buffer. Okay, so CPU inaweza endelea hata kufanya vitu zingine. I can still do other things with the computer as the printer is printing. All right, why? Because all these, they are not now being held by the RAM, they are being held by the buffer of the printer module. Okay, so these modules also act as buffers. Okay, they also act as buffers. And then there is error detection. Error detection is things like detecting whether detecting whether that particular device that has been interconnected, if it is faulty, if it has an issue. For instance, if you connect flash disk in a crash and you connect it to the machine, that IO module, it is able, because it cannot initiate communication between that flash disk you have inserted into the USB port and that flash disk. It cannot initiate communication, so it will detect. It is that module that will detect that that flash disk is faulty. All right, and then it will send that to the processor. That's why we also have processor communication there, right? It will send that kind of information to the processor, and then the processor can generate an error message, and you can see that error message on the screen. Okay, so modules, basically, kazi ya modules, the work of input output modules is basically to initiate that's the primary function, to initiate communication between a peripheral device and a machine. It can be an audio module, it can be a printer module, it can be, and we have already said that even all these ports zenyewe, wacha hata hizi za kununua, wacha modules za kununua, ports zenyewe za computer, they have modules behind them. All right, they have modules behind them, like the USB has a module behind it. The audio jack, the audio port has a module behind it. The what else? The Ethernet cable, the Ethernet the Ethernet port has a module behind it. So all these kind of devices that are called peripheral devices, all those ports where they connect to the machine, they have modules. Okay, and so that is the primary function, plus now are the other functions that we have discussed. Okay, so it's also called an input output interface. It's not a different thing. Okay, it's not a different thing. It's an input output module or an input output interface. Now there are three ways in which transfer of data happens through these interfaces. We are just going to mention them, and then we are going to stop somewhere so that we can take over from the next class. So there are three ways in which data transfer happens through those modules, whether it's a USB module or an audio module or a printer module or a Ethernet module, whatever. there are three modes of transfer that happen that facilitate communication between the processor and the devices connected to those modules. The first mode of transfer in an input-output module is called programmed input-output, programmed I/O. The second is called interrupt-initiated I/O, and the other is called direct memory access I/O. Programmed I/O, interrupt-initiated I/O, and direct memory access input-output DMA. So these are the three modes of transfer that facilitate communication between a device, a peripheral device, and a module and the CPU. Okay, so we are going to discuss each of these in the next classes. I have scheduled this class to end at 1:30, so it is 8 minutes to time. So we're going to continue this from next class so that you can also absorb what we have been able to learn so far. So we stop at this point. Three modes of transfer of through input of modules: programmed I/O, interrupt driven or interrupt initiated I/O, and direct memory access. Okay, so we are going to discuss this in detail in the next classes. So I beg that we stop at that point. If there is any question, you can ask. Any question? All right. If there is no question, then I will dismiss us till next time. So I will also put in the portal. I'm going to upload an assignment 1. I'm going to give assignment 1. So you're going to look for it by evening. It's going to be there, an assignment 1, and also some of the notes that we have discussed today. It's going to be there. So have a good afternoon and enjoy the rest of your day.